Cool, so just letting you guys know now, I've started the recording. What I need to go over today is composite functions. So this lesson, for some students might be a little bit of revision, for some students might be the first time. Some classes haven't quite gone into the depth of composite functions that was needed before your APs. So that's what we're going to discuss today. So hopefully some of you this is familiar and will work as revision. For others, you know, we'll get into it, and to not worry, you've actually done composite functions a lot. You just haven't realized that you've been doing them. So let's jump into it straight away. A composite function, you guys have probably read that little bit of blue there. Is a composite function is a relationship between functions where the output of one function becomes the input of a second function. Yeah, sounds pretty wordy. Actually pretty much means you've got one function, and instead of inputting a number into that function, you're just going to input another function. And we've seen this idea of composite before in mathematics. If we stretch all the way back to year 8, we were introducing finding the areas of composite shapes, where you're putting together multiple shapes to create one new thing. All we're doing here is we're putting together multiple functions to create one new function. So just quickly, if we recap for ourselves, let's go light green. Given the fact that f of x is equal to x squared plus 5x, we've done a lot of substituting before. So we can substitute f of 2 in there, and we know that means that this 2 here means every time you see an x value, just replace it with 2. So we end up with 2 squared plus 5 lots of 2, and that was equal to 14. And that was from one of our examples yesterday. When we went through and we looked at odd and even functions, instead of substituting a number, we got you to substitute in negative x. So every time you saw x, you had to substitute negative x in its place. So again, here we would say it was negative x squared plus 5 lots of negative x, which becomes x squared minus 5x. And again, we looked at that yesterday as well, so hopefully that feels a little bit familiar. Where I want to branch out from this is in this example, this recap example here, where we did our odd and even functions. That's the first time you've actually come across composite functions, that this f of negative x is actually a composite function. And what I mean by that is we can think about this in 2 different ways. I can think that negative x, it's a function in itself, it's a graph. So just quickly on the right here, negative x, if we were to sketch it, I'll do that in a slightly different color. Let's go back. Negative x is just that diagonal line that goes down. So that's what negative x is. Negative x in itself can be a function, and we know it's a function because if we do the vertical line test anywhere along that black line, it's going to pass. So when we substitute negative x in, we've been doing composite functions. Actually, so let's have a look at, let's get into some detail here. f of negative x, if we say f of x was x squared plus 5x, and then we said that g of x, some other function, is just negative x, then you can see what I've got here is I have the function of x, the f, but inside the brackets is what I want to substitute into it. And here this notation says, for the function f, substitute in the function of g. So f of g of x, well, that just becomes, well, with f of x, you're substituting negative x for everywhere, which is what we had earlier, which is what we ended up with, our negative x squared plus 5 lots of negative x. which equals x squared minus 5x. And that now becomes a different function. Is that okay with everyone? That we've seen composite functions before, we've done it by just substituting in, and if we can substitute in a value, we can substitute in any kind of algebraic expression that we want. Any questions on what I've gone through so far? Or we're all comfortable? Hopefully we're all comfortable, because this is things we've seen before. So let's talk about some notation. There are two types of notation that you'll see with composite functions. You'll have f of g of x, and that just means sub g of x into, right? And that's what we've seen earlier, that if I have f of g of x, just substitute the g of x function into f of x. The other notation that we see, and I like to describe it as the fog notation. Fog notation means exactly the same thing. It means sub g of x into f of x. All right. Very similar to if we think back to ratios. Remember when we describe ratios, we describe them in the order that they're stated. If I said John and Jenny share Lotto in a ratio of 3 to 1, John gets 3, Jenny gets 1, because that's the order that I've mentioned it. When we talk about fog notation, the f of g, it's the order. It's, since g is mentioned second, it's the thing that's going inside f. Is that okay? Cool. So hopefully that's fine. A lot of people are saying yes at the moment. So your two types of notation are going to be the f of g of x, which a lot of textbooks tend to roll with that, but there is that notation, and it's mentioned in our syllabus as well, our fog notation that goes in order. Whatever's mentioned second, that after the O, that's what's our input. Cool. Let's jump into some examples. Does anyone want to have a go at thinking what this example would look like? I do realize there's a power of 2, so it might be difficult to type. So if you want to turn your mic on and talk it out loud, that's cool. Yep, so one thing we can think of it is that I'm going to change color. We are going, what I'm actually looking for is, that's what my substitution is going to be. Which, yeah, and I'm looking through it. Everyone's is on fire there. 2x minus 5 all squared. And what do I know about 2x minus 5 all squared? What are some features of that that are interesting to me? It is a perfect square. So because it's a perfect square, what does that mean? What are we talking to? Is it a polynomial? It's a quadratic. It's a polynomial of degree 2. So that's going to give us that parabola shape. It's going to be arms pointing up. It's going to cross our y-axis at positive 25. There's a whole heap of things that we can then go on and ask you after we've asked you to do a composite. After you've done a substitution, we can then ask you to go further on, and I could even now ask you to sketch that function if I wanted to. Is everyone okay with that? Yep, cool. All right, quickly rocking through to our second example here. Something a little bit easy-ish. Familiar. F of x and g of x is x squared plus 3 and x cubed respectively. F of g of x. So f of g of x just means substituting x cubed every time we see x. So we're going to have x cubed squared plus 3. which becomes x to the power of 6 plus 3, and that becomes our new function. Was that okay? I feel that's pretty simple, pretty straightforward at the moment. What I will do, I will give you, do we follow fog every time? Well, here, Rhea, you can see in question 2 here, A and B, one's fog and one's G of F. It just depends how the question's written as what I want you to do. What I might do is I'll give you guys, we got those two pretty equal, maybe what, 3 minutes to have a quick go at finding those two for me. So I'll give you like 3 minutes. Can you find what those two equate to? Cool. So running through that first one, F of G. So it goes done and center first. Let's go. We'll run through it now. F O G. So fog means get the G and substitute it into F. So for the first one, what I'm going to do is I need to put 1 on X into, so effectively what fog means is I'm getting the function F and I'm substituting 1 on X into that function, which is going to be 5 times 1 on X plus 2, which just becomes 5 on X plus 2. So that's our first one there. I had to substitute G into F. And then the second one, I need to substitute F into G. So that's just going to be G of 5x plus 2, which is going to be 1 on 5x plus 2. All right, so we just got to be careful there. Sometimes we like to throw fractions out at you as well and manipulate. And you just got to be really careful and take your time to understand how fractions work. Remember, fractions are our friends. And take the time to substitute things in correctly. Yeah, cool. Do I have anything else? No. All right, so for example, that 3 there, can you find the domain and range of f of g, the fog, given that f of x equals 1 on x and g of x equals 9 on x squared? So I'll give you a second to have a go at that. So start off by substituting it in and then having a look at what does it actually look like. So hopefully everyone was able to get the substitution that we have 1 on 9 minus x squared. I might change that color. I don't like that color. Cool. So hopefully that's fine. So now I've asked you to find the domain and range of that. So what is something important to think about when we talk about domain and range? So let's just start off with domain. Now, before I go any further here, with domain, I haven't specified that you need to use interval notation. I've just asked you for the domain and ranges. So if you wanted to, you could use the less than or equal to, x is less than this or greater than this to describe the domain and range as well if you wanted to. But so you could describe it any way you want to. I'm going to describe it in interval notation. What's important about -3 and 3, Dave? I agree those are very valid numbers that we need to consider. But what about them? They stop. X can't equal, yeah. So one thing to, yeah, so everything's important there, exactly what you talked about that. So at -3 and 3, the equation stops. X can't equal a negative or 0. What we're talking about here is to consider what kind of function do we have, and we have a fraction. And one thing we definitely know about fractions is our denominator can't be 0. And then when we look at our denominator, which is just 9 minus x squared, we know that that cannot equal 0. So when does 9 minus x squared equal 0? Well, that would happen, like Dave said, at -3 and 3. Marcus, I like it. Yeah, so we know that x cannot equal 3 or x cannot equal -3. We know at those 2 points we're going to get a 0, so it can't be that. So our domain is there's every single other x value can exist except for 3 and -3. And if you can see how Marcus has written it, that's the way that our interval notation will work here. So x is going to belong to, it's going to go from -infinity to -3. Remember, I'm using curved brackets because I can't equal 3. And then union with -3 to 3, because in between -3 and 3, the graph's going to exist. And that can be then also union with 3 to, oh, that was pretty dodgy, infinity. And there's our domain. And I'll just quickly show you, because I've used every teacher's favorite friend, Desmos. And there is the graph of 1 on 9 minus x squared. And you can see at -3 and at 3, we have some asymptotes. And the graph exists and behaves differently around those points there. So I'll just... It does. It's pretty cool, the stuff you can do with graphs by just changing something slightly. So I'll come back to my iPad now. The range for that question was just from -infinity to +infinity. There was no horizontal asymptotes. There was no part across the graph where it doesn't exist. It actually existed everywhere in its range. Oh, did it? 0, Alex, yes. I just realized because my numerators are non-zero, that was quite silly of me, wasn't it? I had a special moment there. Apologies. So -infinity to 0, union with 0 to infinity. Thank you for picking that one up. Sorry, my Mac's a little bit slow these days. Ryan, it's coming back. I've had to, my computer decided to restart itself. So hopefully you guys are now seeing my iPad screen back up and running. Yeah, beautiful. Cool. All right. Whew, we're back. All right. So then, yeah, as Alex said there, our range, it doesn't include 0 because it's a fraction and our numerator is not 0, is a non-zero. That means it can never equal 0. 1 divided by something is always going to give us a value. It will never equal 0. So our range is -infinity to 0 and then 0 to infinity. Now, earlier someone asked me what that what that E symbol was. That's just something from set notation. Its proper name escapes me for the moment. I want to say epsilon, but it doesn't feel right, but it does. It just means belongs to the set of. So X with the funny E means X belongs, yes, thank you, element. X is an element belonging to those ranges there. So X belongs from -infinity to -3, -3 to 3, and 3 to infinity. And because we've used our curvy brackets, it doesn't exactly belong at those ones there. So that's that one. What I was going to wrap up on was just one question here and another question. I thought it was a nice one to think about. It's that asking you to think a little bit more about how functions work. So you're given the function f of x is 5x squared minus 5. And we don't know what g of x is, but we know that g of x is a function such that when you substitute f of x back into it, so g of f of x, when you substitute that in, your answer is just 5x squared minus 5. It's just that original function. And that happens for all x. And you've been asked to then define what is g of x? What is that function? Anyone got any thoughts on what's going on there? Is it 1? Ria, I like your thinking, but let's pause for a second there. So let's just throw that out there. I like it. If g of x equals 1, how am I meant to figure out what 5x squared minus 5 is equal to? If there's nothing, if g of x just equals 1, there's no pronumeral, there's no x for me to substitute the f of x function into. But I like your thinking with 1 because 1 is a number that doesn't manipulate anything. Anyone else got any ideas? X. And you're spot on, Alex. If g of x is equal to just x, when I substitute 5x squared minus 5 in, that says wherever I see x, replace it with 5x squared minus 5. And that was equal to f of x. Is that okay? Yeah. So that question there, it's a bit of a reverse question on functions and asking you to think about, well, how do functions operate? And if I substitute something into it, how do I get the exact same answer out of it? That's why I liked your answer, Ria, of 1, because 1 didn't manipulate the value of something, but it didn't give us an opportunity to substitute in. So 1x gave us this value opportunity to substitute in. Cool.